Hello, chemistry students. Today we're going to be talking about concentration and dilution and how they apply to solutions in chemistry. So from the last lab we did in class, we learned that molarity, which is represented as a capital M as a unit, is equal to the moles of solute divided by the volume of solution. So it looks like this. Capital M is equal to moles of solute divided by liters of solution. How much stuff there is dissolved in a certain amount of volume. And we also learned, based off of this, that the moles of solute and the molarity have a directly proportional relationship. If, say, we were to keep the liters of a solution constant and we added more solute to it, the concentration of that solution is going to go up. But say we had a set amount of moles and then we added more volume to the solution, we'd find that the concentration went down, that there is an inversely proportional relationship between the concentration and the volume of the solution, because the more solution you add, the more dilute it gets, and therefore the less stuff there is per amount of volume. So say we had a 2M solution. We'd refer to that as a 2-molar solution. And we could say that it contains 2 moles of solute per 1 liter. So let's use this in some more analytical stuff. So what is the concentration of a 0.4 liter solution containing 0.6 moles? Well, we know that the molarity, the concentration, is the moles of solute over the liters of solution. So in this case, we can divide 0.6 moles by 0.4 liters, and we'll end up with a 1.5 molar solution. So the molar is an interesting unit because it's kind of made up of two smaller units. So you don't really need to do anything to cancel out the units here because moles over liter is equal to molar. Let's do another problem. What is the concentration of a 0.4 liter solution containing 5.4 grams of sodium chloride? Now this one's slightly different because it doesn't directly give us the moles. So we're going to have to determine the moles of the sodium chloride through the molar mass of sodium chloride. So I'm going to have to convert these grams to moles first before I can figure out the molarity. So I do that by dividing the grams by the molar mass of the sodium chloride, which is 58.44. So 5.84 divided by 58.44, that gives us 0.1 moles. And then if I take my 0.1 moles and divide that by the volume of the solution, which was 0.4, that gives me a 0.25 molar solution, or a 0.25 mole per liter solution. Let's do another one. What is the concentration of a 300 milliliter solution containing 21.25 grams of beryllium fluoride? This adds one extra little step to this, since molar is moles per liter and they gave us milliliters. So we're gonna have to do a couple unit conversions here. So first, let's do the let's turn the solution into the right units. So we know that there are 1,000 milliliters in 1 liter. So if we divide 300 milliliters by 1 liter over 1,000, the milliliters will cancel out, and then I'll end up with 0.300 liters. And then I need to figure out the moles of the solute, which we get from the 21.25 grams of beryllium fluoride. So we're going to take the grams and we're going to divide it by the molar mass, which in this case was 47.01. And that gives us 0.45 moles of the beryllium fluoride. And then if I divide the moles of the solute by the liters of the solution, then I finally end up with 1.5 molar. So let's think about something slightly different. If I had a 200 milliliter of a 1 molar solution, what would happen to the concentration if I added another 200 milliliters of water? So in this case, we're not changing the amount of solute that's there, but we are doubling the volume of the solution. So we discussed earlier that there is an inverse relationship between the molarity of a solution and the solution's volume, especially if we're doing a situation where we're keeping the moles of solute steady. We're not adding any more moles of solute in this case. So if we think about it logically, the total volume is doubling, but no moles of solute are added. And since there's an inverse relationship here, we can assume that the concentration is going to go down. Because if you think about it in terms of a ratio, it's moles of solute over liters of solution. If we're increasing the denominator but not changing the numerator, we're going to be dividing by a bigger number, and therefore our total number is going to get smaller. And if we think about this just in terms of common sense, if I had a set amount of stuff and then I doubled the volume of the solution, I have the same amount of things in twice the volume. So you could say that it's half as concentrated. The stuff is spread out into twice the amount of volume. So without doing any math, we can kind of assume that our 1 molar solution is going to turn into a 0.5 molar solution if we double the concentration. There's a way to directly determine this mathematically, though, if it's less easy to do in your head, using the following relationship. So when you're ever diluting a solution in chemistry, which is actually something that happens a lot in chemistry, it's important to be able to make different solutions with different concentrations and to be able to specify the concentration you want by diluting it. It has the following relationship. So this equation is going to be really important. So M1V1 is equal to M2V2. The 1 and 2 refer to a sort of before and after state. So the M1 represents the starting concentration, the starting molarity, or the molarity of the original solution. And the V1 also represents the volume of the original solution. And then the M2 and the V2 are going to represent the molarity and the volume of the new solution that is being created after the dilution. So let's apply this to some situations. So let's revisit that previous problem that we kind of did in our head, that we kind of common sensed an answer to. So we started with a 1 molar solution, and we had a 200 milliliter starting solution, which is equal to 0.2 liters. But one thing you'll notice about this specific equation is it doesn't matter if you use milliliters or liters for the units of the volume, as long as V1 and V2 agree. So say you're solving for V2 and you plug in milliliters for V1, you're going to end up with milliliters for V2. Or if you plug in liters for V1, you're going to get liters for V2 based off of how the units work out. But let's talk about this problem again. So we have a 1 molar starting concentration. We don't know what its final concentration is. We know that it started as 200 milliliters, and then we know that we added 200 milliliters to the solution. So that means that the final volume is going to be 400 because it's 200 plus 200. So then I could set it up. In this case, I'm solving for M2. So I'm going to need to do a little bit of algebra. I highly, 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 highly recommend that you solve your equations symbolically first. What that means is that I take my M1V1 equals M2V2 and I start doing the algebra without even thinking about the numbers, without plugging anything in. I know I want to solve for M2, so I'm going to isolate M2 by dividing both sides by V2. And then what I end up with is M2 is equal to M1V1 over V2. And now I can start plugging in my information. I know I had a 1 molar concentration. I know I started with 0.2 liters. And then I know I ended with 0.4 liters. So 1 times 0.2 divided by 0.4, that gets us the 0.5 molar that we sort of figured out through common sense earlier. Let's do another problem. So say we had a 1.25 molar solution that had a volume of 100 milliliters. I'm going to add 0 there just so we can be better about sig figs. All right, how much water would you need to add to get a 0.25 molar solution? So this is a really good example of the types of problems that come up in chemistry regarding dilution. Like sometimes you want to do an experiment, and that experiment specifies that one of the solutions has a specific concentration. But you go to your chemical supplies and you see that the concentrations of the stuff that you have are totally wrong or are too concentrated, which might make a more violent reaction than you wanted to, or it's a more dangerous substance that you want to deal with. So you're going to want to dilute that solution. And to dilute it from 1.25 to 0.25, I'm going to need a very specific procedure. So I have 1.25 molar solution that is 100 milliliters, and I'm going to want to figure out how much water I need to add to get it to be 0.25. So I'm going to want it to be like 1/5 of its original volume. So that we can kind of assume that we might need to increase the solution volume by times 5, but let's confirm that with the actual math. So we know the formula is M1V1 is equal to M2V2. We can start to label all of the different parts. The starting concentration is 1.25 molar. The starting volume is 0.1 liters. And the final concentration that I want is 0.25 molar. So that means that I'm solving for V2. I'm solving for what the final concentration is going to be. So if I look at my equation, M1V1 is equal to M2V2, I want to solve for V2 so that I can divide both sides by M2 to get there. So therefore, V2 is going to be equal to M1 times V1 over M2. So if I plug that all in, I get 1.25 molar times 0.1 liter divided by 0.25 molar. The molars cancel out, and I get units of liters. And then I'm going to get 0.5 liters as my final volume. And I can't just say that 500 milliliters is the answer to this question, because if we look back at the question, it specifies that it's asking for how much water would we need to add to get to a 0.25 molar solution. So this 500 is our final volume that we want, but we know that based off of the context that we started with 100 milliliters. So to go from 100 milliliters to 500 milliliters, I'm going to need to add 400 milliliters to get there. So that would be the actual answer to this question. All right, let's do another one. So we have 250 milliliters of water, and we're adding that to a, we added 250 milliliters of water to a 100 milliliter solution. And we know that the final concentration is 0.5 molar. I want to know what was the original concentration. So we had sort of an unknown concentration that we started with, and we want to sort of reverse engineer what that original concentration was before we started diluting it. So same equation as before. Let's fill in our variables. Our M1 is unknown. We didn't know what the original concentration was, but we knew that the original solution had a volume of 100 milliliters. My final volume, or for my final concentration, was 0.5 molar. That was given here. And my final volume, I had to sort of figure it out through context because we had 250 milliliters of water that we were adding to 100. So the final volume is going to be the sum of the two. So that's why it's 350 milliliters here. So make sure you're keeping track of that kind of logic based off of what's actually happening in the problem. So now I'm solving for M1, so I can divide both sides by V1. So I'm going to end up with M1 is equal to M2 times V2 over V1. So that means 0.5 molar times 0.350 liters divided by 0.1 liters. That ends up with a 1.75 molar solution, was the concentration of the original solution. And just to remind you again, it doesn't matter if I convert these to liters or not, because 0.5 times 0.350 divided by 0.1 is going to give you the exact same value as 0.5 times 350 divided by 100. And you'll notice that regardless of the volume units, that since there's one on top of the ratio and one on the bottom of the ratio here, they're going to cancel each other out anyways. So 0.350 liters divided by 0.1 liters is the same thing as 350 milliliters divided by 100 milliliters. So hopefully this is enough information to get you going on these problems, and I will see you in the next video.